In 2014, a diamond that formed deep inside the Earth was brought to the surface. It came from hundreds of miles below our feet, far deeper than any drill has ever reached. Inside that diamond was something scientists did not expect. It contained evidence of water, not trapped groundwater, not an underground lake, not a buried sea beneath a continent, something much deeper. For generations, we believed Earth's water was accounted for, oceans mapped, ice sheets measured, rivers tracked, even clouds estimated from orbit. The system seemed complete, but earthquake waves passing through the planet told a different story. Across the globe, they slowed in the same deep layer, a region too hot for liquid water, too compressed for caverns, too deep for exploration. Whatever was there wasn't visible, it wasn't flowing, and yet it behaved as though water was part of the structure itself. If scientists are correct, the largest reservoir of water on Earth may not be on the surface at all. It may be locked inside rock, hundreds of miles down. So, how much of our planet's water have we never truly seen? Tonight, we look beneath the crust into a layer no human has ever touched and examine the possibility that the greatest ocean on Earth is hidden inside stone. But before we begin, if you find peace in these gentle journeys where science drifts like a lullaby, I'd be so grateful if you gave this video a soft like or tapped subscribe so that more curious dreamers can join us here. And if you'd like, let me know in the comments where you're listening from tonight and what time it is there. It's always such a joy to see how far this little sleepy corner of science can travel across the world. Now, take a slow, deep breath. Let your shoulders relax, and together, let's look deeper than we ever have before. Long before we learned to listen to the slow tremors moving through stone, we learned to count what shimmered in the light. The surface of Earth appears generous and complete, wrapped in a vast skin of blue that covers nearly 70% of the planet. The oceans alone hold about 1,300,000,000 cubic kilometers of water, a volume so immense that it shapes climate, coastlines, and the rhythms of life. Their tides are charted with precision, their depths mapped in patient sweeps of sonar, their surfaces traced by satellites that detect changes in height no thicker than a fingernail. Beyond the saltwater expanse lies the smaller fraction we call fresh. Most of it rests in silence, locked within polar ice sheets and high mountain glaciers, preserved in crystalline stillness. A significant portion seeps into the ground, filling pores in sediment and fractures in rock, forming aquifers that stretch beneath plains and forests. Only a delicate sliver gathers in lakes or threads its way through rivers, moving visibly across continents before returning to the sea. When drawn as a diagram, the distribution feels orderly, almost symmetrical, as though every drop has been assigned its place. From childhood lessons, the motion of this water seems elegantly cyclical. Sunlight warms the ocean's surface, lifting vapor into the atmosphere. Air currents carry invisible moisture across vast distances until it condenses into clouds. Rain falls, snow accumulates, streams converge, and rivers wind back toward the coasts. Evaporation, condensation, precipitation, runoff. The sequence is repeated so often that it feels closed and self-contained, a system balanced by gravity and heat. Modern instruments have reinforced this sense of completion. Orbiting satellites measure variations in Earth's gravitational field to estimate shifts in ocean mass. Laser altimeters scan ice sheets to calculate thickness changes down to mere centimeters. River discharge is recorded, groundwater monitored, atmospheric humidity sampled from space. Layer by layer, the accounting has grown more refined. Each improvement in technology has narrowed uncertainty, tightening the margins of error until the global water budget appeared nearly settled. Within this framework, Earth's hydrosphere seemed understood as a surface phenomenon. Water belonged to oceans, ice, rivers, lakes, clouds, and shallow subsurface reservoirs. Its pathways were visible in storms and seasons, its storage measurable by instruments circling far above. The numbers aligned convincingly, reinforcing the idea that the planet's water had been tallied with care. It felt sufficient. The blue surface, the white caps of ice, the flowing arteries of rivers together formed a portrait of completeness. In that portrait, little space remained for anything uncounted, and the story of water appeared to end at the boundary where rock grows too hot and pressure too great for the familiar cycle to continue. Steel has pressed downward into the crust with patience and heat, carving a narrow shaft through ancient rock in a remote corner of northern Europe. The deepest of these attempts reached a little over 12 kilometers before temperature and pressure overwhelmed the machinery. Beneath that depth, the planet remains untouched by drill bits or human hands. Yet the distance from the surface to the center stretches more than 6,300 kilometers, a span so vast that direct exploration fades almost immediately into impossibility. Knowledge of the interior has come instead from motion. When tectonic plates shift and strain releases along a fault, energy ripples outward in waves that travel through the entire globe. These vibrations are subtle at great distances, but sensitive instruments known as seismometers record their arrival with extraordinary precision. Each tremor becomes a messenger, carrying information from regions no one will ever see directly. There are different kinds of seismic waves, and they move in distinct ways. Primary waves compress and expand the material they pass through, pushing particles back and forth in the same direction as travel. Secondary waves shear the material side to side, moving particles perpendicular to their path. The difference is not merely mechanical. Secondary waves cannot move through liquid, while primary waves can pass through both solid and molten regions, though their speed changes depending on density and composition. As earthquakes occur across oceans and continents, networks of instruments capture the timing of each wave's arrival. Some signals arrive sooner than expected, others later. By comparing thousands of these paths, scientists construct a three-dimensional portrait of the planet's interior, where waves accelerate, rock is denser or more rigid. Where they slow, materials may be hotter, partially molten, or chemically distinct. In certain zones, secondary waves vanish entirely, revealing layers that behave like liquid rather than solid. Through this patient listening, the broad architecture of Earth emerged. A thin crust rests upon a vast mantle composed of high-pressure silicate minerals. Deeper still lies an outer core that flows as molten metal, and at the center, a solid inner core forged under immense compression. None of these regions were revealed by excavation. They were inferred from patterns of travel time, refraction, and reflection, the way a physician interprets an internal structure through ultrasound. Seismology has grown more refined over decades, evolving from simple arrival time measurements to global tomography that maps subtle variations in wave speed. The planet is now understood not as a uniform sphere, but as a layered and dynamic body, its interior characterized by boundaries where minerals change structure under pressure. All of this has been learned without crossing more than a thin fraction of the outer shell, by trusting that the Earth itself will speak through vibration when it shifts, and by learning how to translate those vibrations into a coherent image of what lies far below. Between the rigid shell we inhabit and the metallic depths far below, there exists a region defined not by visibility, but by transformation. It does not announce itself with molten rivers or fractured plates. It reveals its presence through change, through the quiet rearrangement of atoms under pressure that steadily increases with depth. This is the mantle transition zone, a band of the planet that rests roughly between 410 and 660 kilometers beneath the surface, suspended between familiarity and extremity. Above it, the upper mantle extends downward from the base of the crust, composed largely of silicate minerals rich in magnesium and iron. Below it, the lower mantle stretches toward the core, denser and more compressed. The transition zone is neither of these domains, yet it is shaped by both. It forms a boundary where pressure becomes strong enough to alter the internal architecture of minerals without melting them. In this realm, familiar compounds adopt new crystalline structures, packing their atoms more tightly as the weight of overlying rock presses downward. One of the defining features of this region is the transformation of olivine, a common mineral in the upper mantle. As depth increases, olivine reorganizes into denser forms, first into wadsleyite and then into ringwoodite. These are not different substances in composition, but different arrangements of the same elements, adjusted to survive in a world of crushing force. The shift is abrupt on geological scales, creating seismic boundaries that reflect and refract earthquake waves, marking the upper and lower limits of the transition zone with remarkable consistency around the globe. Temperatures here are high, yet rock remains solid, flowing slowly over immense spans of time rather than melting into liquid. Pressure reshapes bonds and compresses structures, altering the way minerals interact with heat and volatiles. Chemical behavior shifts subtly. Elements that were once accommodated loosely within crystal lattices may become stabilized in new configurations. The transition zone acts as both a gateway and a reservoir, influencing the movement of material between the shallow mantle and the deeper interior. This band of transformation is critical for understanding the chemistry of the deep earth. It regulates how elements are stored and transported, how density contrasts drive convection, and how internal boundaries influence the long circulation of matter within the planet. Seismic studies reveal it as a global layer, persistent and coherent, yet dynamic in thickness and composition depending on temperature and tectonic setting. In the slow choreography of mantle convection, the transition zone serves as a hinge. Rising plumes and descending slabs encounter its pressure thresholds, altering their behavior as minerals shift form. Within this interval of depth, the planet expresses a delicate balance between structure and change, a reminder that even in regions beyond reach, transformation is constant and quietly profound. In laboratories where fragments of the deep earth are studied beneath steady light, there are minerals that cannot exist in open air for long. Their structures belong to pressures far beyond the surface, to realms where rock is forced into tighter and tighter arrangements. Among these rare forms is ringwoodite, a high-pressure variant of olivine that reveals itself only when conditions mirror those of the mantle transition zone. It is composed of the same fundamental elements as the green crystals found in volcanic rocks, yet its internal architecture is transformed, compacted into a denser spinel structure capable of surviving extraordinary compression. Ringwoodite does not form in the crust or in shallow magma chambers. It crystallizes hundreds of kilometers down, where temperature and pressure converge in precise balance. For decades, its existence was known primarily from laboratory experiments and from meteorites that experienced shock during ancient impacts. Scientists could reproduce it in high-pressure devices, confirming its stability at depths corresponding to the transition zone, but natural samples from Earth itself remained elusive. That changed when a diamond carried a fragment of this hidden world upward. Diamonds form deep within the mantle, and can encapsulate tiny inclusions as they crystallize, sealing them away like time capsules. In a stone recovered from Brazil, researchers identified a minute inclusion of ringwoodite. Within that inclusion, spectroscopic analysis detected hydroxyl groups embedded in the mineral's lattice. The hydrogen and oxygen were not present as droplets or fluid pockets. They were chemically bound within the crystal structure, occupying sites normally filled by oxygen in the silicate framework. This detail was subtle yet profound. Hydroxyl in ringwoodite indicates that the mineral can incorporate water into its very architecture, not as liquid, but as a structural component. Under the immense pressures of the transition zone, hydrogen atoms can substitute into defects within the lattice, stabilizing the crystal while storing significant amounts of water by weight. The mineral remains solid, its geometry intact, yet it carries within it the elemental ingredients of water dispersed at the atomic scale. Because ringwoodite is stable only within a specific depth interval, its capacity to host hydroxyl suggests that the transition zone itself could serve as a vast reservoir. If large volumes of this mineral are hydrated, the cumulative storage becomes considerable. The discovery inside that single diamond provided direct physical evidence supporting interpretations drawn from seismic observations. It linked mineral physics to planetary scale implications, demonstrating that water need not pool or flow to exist in abundance. Instead, it can reside quietly within stone, integrated into the crystalline bones of the earth, waiting to be inferred through careful study rather than seen with the eye. Deep within the mantle, carbon is subjected to such immense pressure that it crystallizes into diamond, forming in darkness and heat long before it ever approaches the surface. As these crystals grow, they sometimes trap microscopic fragments of their surroundings, sealing them within an unyielding lattice. These inclusions are not flaws in the gemstone. They are preserved samples of an environment otherwise beyond reach, protected from later alteration by the diamond's remarkable strength and chemical resistance. When volcanic forces eventually propel certain diamonds upward in explosive eruptions, they carry those tiny inclusions with them. Most remain too small to notice without careful examination, but under magnification, they reveal minerals that cannot survive at the surface. In one such diamond recovered from Brazil, researchers identified an inclusion of ringwoodite. Its presence alone was extraordinary, since ringwoodite is stable only at the pressures found hundreds of kilometers beneath the crust. The crystal inside the diamond had formed in the mantle transition zone and had been transported intact through layers where it would normally transform into other mineral phases. Laboratory analysis of this inclusion went further. Using infrared spectroscopy, scientists detected hydroxyl within the ringwoodite structure. The signal indicated that hydrogen and oxygen were incorporated into the mineral's lattice, not as fluid trapped in cracks, but as chemically bound components distributed at the atomic level. This observation provided direct physical evidence that water, in the form of hydroxyl, exists in the deep mantle. Until this discovery, much of the case for deep mantle hydration rested on indirect interpretation. Seismic studies had revealed anomalies in wave speeds within the transition zone, patterns consistent with minerals containing water. Experimental mineral physics suggested that ringwoodite could store significant amounts of hydroxyl under high pressure. Yet, without a natural terrestrial sample, the argument remained inferential. The Brazilian diamond bridged that gap between theory and tangible proof. Its significance lay not in size, but in context. A microscopic inclusion confirmed that the transition zone is capable of holding water within its mineral framework. It validated models that connected slowed seismic waves to hydrated phases. It demonstrated that the planet's interior is not chemically dry at those depths, but participates in a more complex exchange between surface and mantle than previously assumed. The diamond itself appeared ordinary to the untrained eye, but inside it carried a message from a realm no drill can access. In its crystalline embrace, a fragment of ringwoodite endured the journey upward, preserving within its structure the quiet testimony that water can reside far below the oceans, woven into the very fabric of deep earth minerals. Across continents and beneath oceans, networks of instruments remain still for long stretches of time, waiting for the planet to shift. When it does, even slightly, vibrations radiate outward in expanding arcs, crossing boundaries that no human will ever approach. These signals pass through layers already described in broad form, yet within one particular depth range, their behavior grows subtly unusual. The waves do not stop, they do not vanish, they hesitate. Primary waves, sensitive to compression, tend to slow when the material they traverse contains hydroxyl within its mineral structure. Laboratory experiments have shown that even small amounts of chemically bound water can reduce seismic velocities by altering rigidity and density at the atomic scale. In the mantle transition zone, where minerals adopt high pressure forms, this effect becomes measurable. When wave paths intersect regions enriched in hydrated phases, arrival times stretch slightly beyond expectations drawn from dry models. As seismologists compiled records from earthquakes occurring around the globe, a pattern began to emerge. Beneath multiple tectonic settings, within the depth interval already known for mineral transformations, seismic velocities appeared lower than predicted. The anomaly was not confined to a single region. It showed up beneath subduction zones, beneath stable continental interiors, beneath ocean basins. The consistency suggested a widespread property rather than a localized irregularity. To interpret these deviations, scientists constructed computational models of the mantle transition zone. They adjusted variables such as temperature, composition, and water content, calculating how each factor would influence wave speeds. By comparing simulated travel times with observed data, they could estimate the degree of hydration required to produce the measured slowdown. The exercise required caution since temperature variations can also reduce seismic velocities. Yet, even after accounting for thermal effects, the remaining discrepancy pointed toward the presence of hydroxyl bearing minerals. The modeled quantities were not trivial. If large volumes of ringwoodite and related phases within the transition zone contained modest weight percentages of water, the cumulative storage could rival or exceed the total mass of water at the surface. The implication did not rely on visible reservoirs or cavities. It arose from the integrated response of minerals distributed across a global layer, hundreds of kilometers thick. These conclusions were not drawn from a single earthquake or a solitary dataset. They developed gradually as global seismic networks expanded and resolution improved. Each new event added another line to the emerging portrait, refining estimates and narrowing uncertainties. The slowdown of waves became more than a curiosity. It became a signal woven through the planet's interior, consistent with a hydrated transition zone that subtly reshapes the passage of energy through stone, hinting at a scale of hidden water far greater than surface accounting alone had ever implied. Far below the drifting continents and far beneath the familiar cycle of clouds and rain, the word water begins to lose its ordinary meaning. At depths approaching 600 kilometers, There are no caverns filled with waves, no hidden seas pressed against stone. Temperature rises into ranges that would flash surface water into vapor, while pressure increases until rock itself becomes denser than steel. In such an environment, liquid as we know it cannot persist in open spaces. The conditions simply do not allow for it. And yet, the essential components of water, hydrogen and oxygen, remain present. They are not gathered into droplets or reservoirs. Instead, they are threaded into the atomic frameworks of minerals stable at those depths. Within the crystal lattice of high-pressure silicates, tiny imperfections and structural sites can host hydroxyl groups. A hydrogen atom bonds with oxygen already embedded in the mineral, forming a unit that resembles water in composition, though not in state. The result is a solid that carries water not as fluid, but as part of its architecture. Under immense compression, matter behaves differently than it does near the surface. Atoms are forced closer together, and the spaces within crystal structures shrink. Bonds rearrange to accommodate stress. In some minerals of the transition zone, this rearrangement creates positions where hydrogen can be stabilized. Laboratory experiments using diamond anvil cells have demonstrated that minerals such as ringwoodite can incorporate significant amounts of hydroxyl when subjected to pressures equivalent to those hundreds of kilometers down. The mineral remains solid and crystalline, yet its physical properties shift subtly with hydration. This distinction matters. Liquid water flows and pools. It exerts pressure against its container and responds readily to gravity. Chemically bound water does none of these things. It does not slosh. It does not carve channels. It is locked in place until temperature or pressure conditions change enough to release it through metamorphic reactions. At depth, the concept of a hidden ocean must therefore be reimagined. The reservoir is dispersed at the microscopic scale, distributed through vast volumes of rock rather than concentrated in voids. High-pressure physics reveals that water's identity is flexible. In extreme environments, its familiar phase diagram expands into domains rarely encountered at the surface. Supercritical states, altered melting points, and shifts in compressibility redefine its behavior. In the mantle transition zone, however, the most consequential transformation is structural. Water becomes part of stone, influencing elasticity, density, and melting behavior without ever appearing as liquid. Understanding this subtle form of storage allows the deep earth to be seen not as a dry furnace beneath a wet shell, but as a chemically interconnected system. The water present there is quiet and immobile on human timescales, yet it participates in a larger circulation that links the interior to the surface over spans measured not in years, but in geological epochs. Scale, at these depths, is not something that can be pictured easily. It must be assembled from weight percentages, mineral proportions, and the sheer thickness of the layer in question. The mantle transition zone extends for hundreds of kilometers around the entire planet, forming a spherical shell between the upper and lower mantle. Within that shell, high-pressure minerals such as wadsleyite and ringwoodite can incorporate hydroxyl into their structures, sometimes at levels approaching a few percent by weight under laboratory conditions. When those percentages are multiplied across such an immense volume of rock, the totals begin to stretch the imagination. If the transition zone were close to full hydration, models suggest it could contain an amount of water comparable to multiple surface oceans. Even if the average water content were far lower than laboratory maxima, the cumulative storage would still be vast. The calculation does not require lakes or flowing reservoirs. It depends only on the widespread distribution of hydrated minerals throughout a layer that encircles the globe. Yet the estimates are not singular. They vary depending on assumptions about temperature, mineral composition, and the degree to which subducted material has introduced water into different regions. Seismic interpretations provide indirect constraints, but they cannot measure water content directly. Experimental results, conducted at high pressure and temperature, offer guidance, though natural conditions may differ subtly from controlled environments. As a result, scientists speak in ranges rather than fixed totals. Some models propose that the transition zone could hold roughly the equivalent of one ocean mass. Others allow for the possibility of several times that amount if hydration is extensive. Conservative interpretations, designed to avoid overstatement, still yield figures that rival the volume of water at the surface. Even at the lower end of these ranges, the implication remains significant. A hidden reservoir of such magnitude would reshape the understanding of Earth's long-term water distribution. Caution persists because direct sampling is limited to rare inclusions and indirect geophysical signals. The planet does not reveal its interior in straightforward measurements. It offers clues that must be pieced together from seismic velocities, mineral physics, and thermodynamic modeling. Each dataset carries uncertainty, and each assumption introduces variability. The resulting picture is therefore probabilistic rather than absolute. Even within those bounds, the scale is striking. The idea that a band of rock hundreds of kilometers below our feet could store water comparable to the oceans challenges the intuitive separation between surface and interior. The numbers, expressed in percentages and global volumes, do not produce dramatic images. Instead, they suggest a quiet immensity, a planetary reservoir dispersed through crystalline structures, immense not because it can be seen, but because of the volume of Earth it quietly occupies. Along the margins of continents and beneath long arcs of islands, the ocean floor bends and descends into the mantle. These subduction zones mark places where one tectonic plate slides beneath another, carrying with it sediments, altered basalt, and fragments of hydrated lithosphere. Long before the descent begins, seawater has already reacted with the oceanic crust. Through fractures and faults, water infiltrates the upper layers of basalt and peridotite, forming minerals that incorporate hydroxyl within their structures. By the time the plate approaches a trench, it carries within it a hidden cargo bound in stone. As the slab sinks deeper, pressure and temperature increase. Minerals that were stable near the surface begin to transform, releasing some of their stored water through dehydration reactions. The liberated fluids rise into the overlying mantle wedge, lowering the melting point of surrounding rock. Partial melting follows, generating magma that is less dense than its surroundings and therefore buoyant. Over time, this magma ascends, feeding volcanic arcs that line subduction zones across the planet. In this way, water that once resided in the ocean is transported downward, chemically integrated into minerals, then released again to influence melting and volcanism. Some of it returns to the surface through volcanic gases and eruptive plumes, rejoining the atmosphere and hydrosphere. Some may travel deeper still, carried past the depths where initial dehydration occurs, entering the transition zone where high-pressure minerals can once again store hydroxyl within their lattices. This exchange unfolds slowly, measured not in seasons or centuries, but across spans approaching 1 billion years. Plates form at mid-ocean ridges, drift across basins, and eventually descend. The water they incorporate during their lifetime becomes part of a long circulation linking surface reservoirs to the mantle interior. Volcanic emissions release water vapor that condenses into clouds, falls as rain, and ultimately flows back toward the sea, completing a circuit that extends far below visible boundaries. The surface and mantle are therefore not isolated domains. They are connected by a dynamic system in which water acts as both participant and mediator. It influences melting temperatures, affects the viscosity of rock, and shapes the behavior of tectonic plates. At the same time, tectonic motion governs how much water is transported downward and how much is returned upward through magmatic processes. This deep water cycle operates quietly beneath the familiar hydrologic cycle taught in classrooms, while evaporation and rainfall trace short-term movements at the surface. Subduction and volcanism trace far longer arcs through the planet's interior. Together, they form a continuous exchange, an enduring circulation that has persisted for much of Earth's history, linking ocean, crust, and mantle in a slow and steady planetary rhythm. Pressure alone does not determine how rock behaves in the deep interior. Composition matters, temperature matters, and so does the quiet presence of hydrogen bound within mineral structures. Even in small amounts, water alters the physical character of mantle material in ways that ripple outward through tectonic systems. It does not pool or flow at these depths, yet its chemical integration into crystals changes how stone responds to heat and stress. One of the most significant effects of water in mantle minerals is the reduction of melting temperature. Dry peridotite requires higher temperatures to begin partial melting, but when hydroxyl is incorporated into its structure, bonds weaken slightly. The energy needed to initiate melting decreases. In subduction settings where fluids are released from descending slabs, this lowering of the melting point allows magma to form more readily in the overlying mantle wedge. The result is not explosive chaos everywhere, but a focused generation of melt that feeds volcanic arcs along convergent boundaries. Water also influences viscosity, the resistance of a material to flow. Though mantle rock remains solid on short timescales, over millions of years it behaves like a slow-moving fluid. Hydrated minerals tend to deform more easily under stress than their dry counterparts. The presence of hydroxyl facilitates dislocation movement within crystal lattices, allowing rock to creep at lower differential stresses. This increased ductility affects convection patterns within the mantle, subtly shaping how heat is transported from the deep interior toward the surface. Plate tectonics depends on contrasts in strength and density. The lithosphere must be rigid enough to fracture and move as coherent plates, while the underlying asthenosphere must be weak enough to permit motion. Water contributes to this balance. In regions where mantle material is hydrated, reduced viscosity can localize deformation, influencing where plates bend, where faults initiate, and how slabs descend. The lubrication provided by chemically bound water is not literal in the everyday sense, yet it softens the mechanical response of rock under prolonged stress. Earthquake behavior is also connected to hydration. At certain depths within subducting slabs, dehydration reactions release fluids that can alter pore pressures and trigger brittle failure in otherwise ductile environments. Some deep focus earthquakes are thought to be linked to these transformations, where the breakdown of hydrous minerals changes the internal stress state of the slab. Even in the transition zone, variations in water content may affect how strain accumulates and is released. Volcanic systems, tectonic boundaries, and mantle convection are therefore entwined with the distribution of water in rock. What appears as solid stone is chemically responsive to the presence of hydrogen and oxygen within its lattice. Over geological timescales, this subtle modification shapes the mobility of plates, the generation of magma, and the seismic character of the planet, revealing water not merely as a surface ingredient of life, but as a deep agent of geological change. There is a restlessness to this planet that is easy to overlook from the steadiness of a shoreline. Continents drift, mountains rise and erode, ocean basins open and close, all with a patience measured in millions of years. This motion is not inevitable for every rocky world. It depends on a delicate balance of strength and weakness within the outer shell, a balance shaped in part by the quiet presence of water within rock. Plate tectonics requires the lithosphere to fracture into moving plates while allowing the underlying mantle to deform slowly enough to accommodate that motion. If the mantle were too rigid, plates would struggle to subduct and recycle. If it were too weak everywhere, coherent plates might never form. Water influences this balance at multiple depths. Chemically bound within minerals, it reduces viscosity and lowers melting temperatures, softening the mantle just enough to permit long-term flow. In this sense, water acts as a subtle softener, not dissolving stone, but easing its resistance to deformation. On worlds where internal water is scarce or absent, tectonic behavior can diverge dramatically. Mars, smaller and cooler, appears to have lost most of its internal heat early in its history. Its surface preserves enormous volcanoes and vast plains, yet there is little evidence of ongoing plate tectonics. Without sustained hydration and sufficient internal energy, its lithosphere thickened and motion slowed, leaving a largely static shell. Venus offers a different contrast. Similar in size to Earth, it retains significant internal heat, yet its surface shows no clear pattern of plate boundaries like those found on Earth. Instead, its crust may behave as a single, stagnant lid, periodically resurfaced by large-scale volcanic events. The extreme surface temperatures on Venus likely prevent stable liquid water, and without substantial hydration in the lithosphere and upper mantle, the mechanical conditions required for plate tectonics may never fully develop. Earth occupies a narrower path. It possesses enough internal heat to drive convection and enough water, both at the surface and stored within the mantle, to moderate the strength of its outer layers. Subduction zones recycle crust into the interior, while mid-ocean ridges generate new lithosphere. This continual renewal regulates the distribution of heat and contributes to long-term carbon cycling, influencing climate stability over immense spans of time. Deep water, dispersed within minerals of the mantle, participates in this enduring process. It helps maintain the conditions under which plates can bend, descend, and be reborn. The result is a geologically alive planet, neither frozen into rigidity nor consumed by unchecked volcanism, but sustained in a dynamic equilibrium where internal circulation and surface habitability remain intertwined across the long arc of Earth's history. Long before continents assembled and oceans settled into familiar basins, the young Earth was a sphere of heat and collision. In those early epochs, material from across the forming solar system converged, bringing with it silicates, metals, and volatile compounds. The origin of Earth's water has been traced back to this turbulent beginning, and for decades, scientists weighed competing possibilities, searching for the primary source of the planet's vast hydrosphere. One early idea favored comets, icy bodies from the outer solar system rich in frozen water. Their impacts, during a period of intense bombardment, could have delivered significant quantities of ice to the hot surface, where it would vaporize and later condense as the planet cooled. Yet, detailed measurements complicated this picture. The ratio of deuterium to hydrogen in many comets differs from that found in Earth's oceans. Deuterium, a heavier isotope of hydrogen, acts as a fingerprint, allowing researchers to compare sources. In several comet samples, the isotopic signature did not align closely with terrestrial water. Attention then turned to carbonaceous asteroids, smaller rocky bodies that also contain hydrated minerals. Meteorites derived from such asteroids exhibit deuterium to hydrogen ratios more similar to ocean water. These findings suggest that much of Earth's water may have been delivered not by distant icy comets, but by impacts from volatile rich asteroids originating closer to the inner solar system. Their collisions would have supplied both water and organic compounds during the planet's formative stages. Yet, delivery from space may not tell the whole story. Some models propose that a portion of Earth's water was incorporated during its initial accretion. Even within the protoplanetary disk near the young sun, certain minerals could bind hydroxyl within their structures. As planetesimals merged to form the growing Earth, these hydrated materials may have become trapped within the mantle. Over time, differentiation and volcanic outgassing would release part of this primordial water to the surface, contributing to the formation of early oceans. The deep mantle, particularly within the transition zone, may still preserve fragments of that ancient inventory. Water stored as hydroxyl in high-pressure minerals could represent material that has remained isolated for billions of years, shielded from the surface cycle. In this sense, the hidden reservoir discussed earlier may not only be a product of ongoing subduction, but also a repository of water present since the planet's infancy. Isotopic studies continue to refine this narrative, comparing hydrogen signatures in mantle-derived rocks with those in surface reservoirs. The emerging picture is one of mixed origins, with contributions from asteroidal impacts and internal retention. Earth's water likely arrived through multiple pathways, some delivered violently from space, others woven quietly into the planet as it formed, later circulating between surface and interior in a story that spans nearly the entire history of the world. There are moments in planetary history that leave no visible trace at the surface, yet remain preserved in the interior like faint memories held in stone. Deep within the mantle, far below the reach of erosion and weather, some portion of Earth's water may have endured since the earliest stages of formation. Before stable oceans spread across cooling crust, before continents assembled and drifted apart, hydrogen and oxygen were already being incorporated into minerals under immense pressure. As the young planet accreted from countless collisions, temperatures soared high enough to melt large regions of its interior. In this molten state, differentiation separated heavy metals toward the core and silicates toward the mantle. Volatile elements, including hydrogen, were partitioned between melt and mineral phases. While some water was lost to space during energetic impacts, not all of it escaped. Certain minerals were capable of retaining hydroxyl even amid the chaos of early heating, trapping traces of primordial water within their crystalline frameworks. Over time, as the surface cooled and volcanic outgassing released vapor into the atmosphere, condensation formed the first long-lasting oceans. Rain fell upon newly solidified crust, filling basins and carving the earliest landscapes. Yet, beneath this emerging hydrosphere, parts of the mantle may have continued to store water that had never participated in that surface cycle. Isolated from evaporation and subduction, shielded by depth and pressure, this ancient inventory could remain largely unchanged for billions of years. Geochemical studies of mantle-derived rocks offer hints of this possibility. Certain isotopic signatures in volcanic basalts suggest the presence of reservoirs that have been only partially mixed with the convecting mantle. These domains may preserve characteristics dating back to the planet's infancy. If they contain water, then that water predates not only modern oceans, but perhaps the stable surface conditions that allowed life to arise. The existence of such primordial water carries implications for early Earth. It suggests that the planet did not rely solely on late delivery from space to acquire its hydrosphere. Instead, part of its water budget may have been inherent from the beginning, integrated into the building blocks of the planet itself. As tectonic processes developed and the deep water cycle began linking surface and mantle, some of this ancient water could have been gradually released, contributing to the maintenance of oceans over immense spans of time. In this view, the oceans visible today are not merely the product of surface processes or external impacts. They are connected to a deeper lineage, one that extends back to the era of planetary assembly. Hidden within high pressure minerals, water older than the seas may still reside, a quiet remnant of the world's earliest chapter carried forward through geological time within the enduring structure of the mantle. The young sun did not shine with the same steadiness it does today. In its earliest stages, solar output fluctuated, and the infant Earth endured a barrage of impacts that repeatedly reheated its surface. Magma oceans may have formed more than once, erasing early crust and releasing vast quantities of vapor into the atmosphere. Under such conditions, liquid water could not remain stable for long. It would have existed as steam, rising and condensing only as temperatures gradually declined. Even after the most violent era of impacts subsided, the planet continued to radiate internal heat left over from accretion and radioactive decay. Volcanic outgassing thickened the atmosphere with carbon dioxide and water vapor. The balance between incoming solar radiation and outgoing heat determined whether oceans could condense and persist. Small shifts in this balance might have tipped the surface toward evaporation or condensation, depending on atmospheric composition and cloud feedbacks. Over geological time, the sun's luminosity has increased gradually. In Earth's distant future, this brightening will intensify evaporation and could eventually threaten the stability of surface oceans. Models of planetary climate suggest that runaway greenhouse conditions are possible when water vapor becomes a dominant greenhouse gas, trapping heat and accelerating warming. Venus may represent an extreme outcome of such a process, where early heating and the loss of water vapor to space left a dry and hostile surface. Against this backdrop of vulnerability, the deep mantle reservoir offers a different perspective. Water stored within high-pressure minerals does not evaporate under surface heating. It remains chemically bound, insulated by hundreds of kilometers of rock. Through subduction, some portion of surface water is transported downward and incorporated into the transition zone. Through volcanism, a fraction is returned. This exchange unfolds slowly, but it provides a mechanism by which water can be cycled away from transient surface extremes. In periods of intense heating or large impacts, some surface water may have been lost to space, particularly if hydrogen escaped from the upper atmosphere. Yet, if substantial quantities were already stored in the mantle, the planet retained a hidden supply. Over time, tectonic and volcanic processes could release portions of that deep inventory, replenishing oceans diminished by loss. The possibility that deep storage acted as a buffer does not imply perfect protection. It suggests resilience. A planet with internal water distributed through its mantle possesses a reserve that is less susceptible to immediate atmospheric escape. In this sense, the hidden reservoir beneath the crust may have contributed to the long-term persistence of surface oceans, moderating the extremes of solar evolution and impact history. and allowing water to endure through cycles of heating and cooling across billions of years. For much of scientific history, the deep interior of the planet was a matter of inference and imagination. Human exploration extended across oceans and into the upper atmosphere long before it penetrated even a small fraction of the crust. Drilling projects reached impressive depths by engineering standards, yet compared to the thousands of kilometers between surface and core, those achievements barely scratched the outer shell. The physical barrier alone ensured that direct sampling of the mantle transition zone would remain beyond reach. Early seismology offered a way to peer inward, but its tools were limited. The first instruments recorded only the most obvious arrivals from large earthquakes. Global coverage was sparse, and data resolution was coarse. Scientists could identify major boundaries such as the crust, mantle, and core, yet subtle variations within the mantle were more difficult to resolve. The transition zone was recognized through changes in seismic wave behavior, but the capacity to interpret those changes in terms of water content required decades of refinement. Computational power also constrained earlier efforts. Modeling how seismic waves propagate through a heterogeneous planet involves solving complex equations across vast datasets. Before the development of advanced computing, such modeling was simplified, often assuming uniform compositions. As digital networks expanded and data processing improved, seismologists began constructing three-dimensional tomographic images of the mantle, revealing patterns that were previously invisible. At the same time, mineral physics underwent its own transformation. High-pressure laboratory techniques matured, allowing researchers to recreate conditions equivalent to those hundreds of kilometers beneath the surface. Diamond anvil cells compressed tiny samples between the tips of gem-quality diamonds, generating pressures comparable to those in the transition zone. Laser heating systems elevated temperatures while spectroscopic tools measured structural changes in real time. Through these experiments, scientists confirmed that minerals like ringwoodite could incorporate significant amounts of hydroxyl under relevant conditions. Earlier generations lacked this experimental confirmation. Without it, seismic anomalies could not be confidently attributed to hydration rather than temperature or compositional variation. Only when laboratory measurements, seismic observations, and computational models converged did the interpretation gain strength. The discovery of hydrated ringwoodite within a natural diamond further bridged the gap between theory and evidence, providing a physical anchor for ideas that had been developing quietly in parallel fields. Scientific understanding often advances not through a single breakthrough, but through the gradual alignment of methods. Improved instrumentation, expanded global networks, sophisticated simulations, and high-pressure experiments each contributed a piece of the puzzle. The hidden reservoir was not overlooked because it was insignificant. It remained concealed because the tools required to perceive it clearly had not yet matured. As those tools evolved, the interior of the planet became less abstract, and the subtle presence of water in deep minerals emerged from the background of uncertainty into clearer view. At depths where pressure mounts far beyond anything encountered at the surface, familiar substances begin to adopt unfamiliar identities. Water, so easily recognized as liquid, vapor, or ice in everyday experience, enters regimes where its phase boundaries shift and its behavior becomes less intuitive. Temperature and pressure together redraw the map of its possible states, expanding into territories rarely seen outside laboratories designed to imitate the deep earth. Under sufficiently high pressure, water can exist as a supercritical fluid, neither purely liquid nor purely gas. In this state, the distinction between phases dissolves. Density approaches that of a liquid, yet the fluid diffuses like a gas, penetrating materials and dissolving substances with unusual efficiency. Though such conditions are more common in certain industrial settings and planetary interiors than in daily life, they reveal that water's properties are not fixed, but responsive to the environment surrounding it. Within the mantle transition zone, however, water most often appears not as free fluid, but as hydroxyl integrated into mineral lattices. Even so, the concept of phase change remains relevant. As pressure increases, hydrogen bonding networks rearrange, molecular distances contract, the compressibility of water decreases, and its melting curve shifts to higher temperatures. Ice itself adopts multiple crystalline forms under compression, far denser than the hexagonal structure that floats in a winter pond. These high-pressure ice phases illustrate how profoundly atomic geometry can transform under stress. To explore such conditions, scientists rely on devices capable of reproducing extreme environments within controlled spaces. Diamond anvil cells are among the most important of these tools. Two opposing diamond tips press against a tiny sample, generating pressures comparable to those hundreds of kilometers below the surface. Because diamonds are transparent, lasers and spectroscopic instruments can probe the compressed material, measuring structural changes and vibrational modes in real time. Heating elements raise temperatures to values consistent with mantle conditions, allowing researchers to observe how minerals and fluids respond together. Through these experiments, it becomes clear that water under extreme pressure is not a simple extension of its surface form. Its molecular behavior shifts in ways that influence melting points, diffusion rates, and chemical reactivity. In high-pressure silicates, hydrogen can occupy interstitial sites, modifying elasticity and density. In partially molten systems, supercritical fluids can enhance transport of elements and facilitate reactions that would proceed more slowly in dry conditions. By recreating fragments of the deep earth within laboratory chambers, scientists translate the abstract language of pressure and temperature into measurable phenomena. The results reveal that water's identity is fluid in more than one sense, adapting to the constraints of its surroundings. In the mantle, this adaptability allows it to persist not as an ocean or vapor, but as a transformative presence embedded within the solid framework of the planet itself. Along the great arcs where continents meet the sea, the boundary between plates tilts downward and disappears into shadow. Oceanic lithosphere, forged at spreading ridges and cooled over millions of years, grows dense enough to sink back into the mantle from which it came. This descent is not abrupt on human timescales, yet in geological perspective, it is steady and persistent, drawing entire slabs of crust and uppermost mantle into the interior. Before the plunge begins, seawater has already altered the oceanic plate. As basalt cools and fractures near mid-ocean ridges, circulating water penetrates its cracks, reacting with minerals to form hydrous phases such as serpentine and amphibole. Even deeper within the lithospheric mantle, peridotite can become hydrated through similar processes. These transformations bind water chemically within mineral structures, incorporating hydroxyl into lattices that will accompany the slab as it sinks. As subduction carries this hydrated material downward, pressure and temperature rise along a path determined by the slab's age and speed. At certain depths, specific hydrous minerals become unstable. Their crystal structures can no longer accommodate hydroxyl under the new conditions, and dehydration reactions occur. Water is expelled not as a vast reservoir, but as fluids migrating through pores and along grain boundaries. These released fluids ascend into the overlying mantle wedge, altering its chemistry and physical properties. The arrival of water-rich fluids lowers the melting point of surrounding mantle rock, encouraging partial melting that would not occur in a completely dry system. Magma forms and begins its ascent, eventually feeding volcanic arcs aligned above the subducting plate. In this way, water that once circulated through oceanic crust influences surface volcanism after a journey deep into the mantle. Not all water is liberated at shallow levels. Some minerals stable at greater depths can retain hydroxyl beyond the initial dehydration stages, allowing portions of the slab's water to penetrate further into the transition zone. There, under higher pressure conditions, new high-pressure phases may incorporate water once more into their structures. The path is complex, marked by intervals of release and intervals of retention, governed by mineral stability fields and thermal gradients. Subduction zones thus serve as gateways through which surface water is transported downward. They are dynamic conduits, linking ocean basins to the deep interior. The sinking slab carries its chemically bound cargo with it, and through a sequence of reactions controlled by pressure and temperature, water is redistributed between phases and depths. This ongoing descent forms one half of a long exchange, a quiet movement of water from the familiar realm of seas and sediments into the layered depths of the mantle. Above the descending slabs of oceanic crust, a different kind of ascent unfolds. Beneath long chains of mountains and island arcs, heat and pressure converge in a mantle wedge enriched by fluids rising from the subducting plate. The water released at depth does not gather into vast pools. It diffuses through rock, moving along grain boundaries, altering minerals, and lowering the temperature at which melting begins. In this subtle way, chemically bound water becomes an agent of transformation. When mantle peridotite encounters these water-rich fluids, its melting point decreases significantly compared to dry conditions. Partial melting initiates at temperatures that would otherwise leave the rock solid. Small fractions of melt accumulate, coalescing into buoyant magma that begins to migrate upward. The melt is less dense than the surrounding mantle, and over time it exploits fractures and zones of weakness ascending through the overlying crust. This process gives rise to volcanic arcs that trace the geometry of subduction zones. From the Andes to the Cascades, from Japan to the islands of the Western Pacific, lines of volcanoes stand as surface expressions of deeper exchange. Their positions are not random. They align above depths where dehydration reactions occur within the descending slab, marking the region where released water most effectively induces melting in the mantle wedge. As magma rises, it evolves. It may stall in crustal chambers, differentiating chemically as crystals form and settle. It may erupt explosively if gases accumulate, or flow more quietly as lava if conditions allow. In either case, water plays a central role, influencing viscosity, gas content, and eruptive style. Volcanic plumes release steam and other volatiles into the atmosphere, returning water that once traveled downward with oceanic crust back to the surface environment. This upward movement is not rapid on planetary timescales. It unfolds over millions of years, part of the larger deep water cycle that links ocean basins to the mantle interior and back again. The hidden reservoir stored within minerals of the transition zone does not empty in sudden bursts. Instead, through countless subduction and melting events, portions of that deep inventory gradually re-enter the surface system. Volcanic arcs, therefore, represent more than dramatic landscapes. They are conduits in a long circulation, where water integrated into stone at great depth influences melting, rises with magma, and eventually returns to air and sea. The visible eruptions are only the final stage of a journey that began far below, where water was bound within minerals under immense pressure, awaiting its slow return through the planet's dynamic interior. Not all earthquakes rupture the brittle crust near the surface. Some originate far deeper, within regions where pressure is so immense that rock is expected to deform slowly rather than fracture. These deep focus earthquakes, occurring hundreds of kilometers below the surface, have long puzzled scientists. Under such conditions, the conventional model of sudden brittle failure should not easily apply. Yet, seismic records reveal sharp ruptures emerging from depths within descending slabs and even near the mantle transition zone. Water, integrated into minerals carried downward by subduction, plays a subtle but significant role in this phenomenon. As hydrated oceanic lithosphere sinks, it encounters rising temperatures and pressures that destabilize certain hydrous phases. Dehydration reactions release fluids from within the crystal structures of minerals such as lawsonite and serpentine. The liberated water does not remain in large cavities. It migrates through microscopic pathways, altering pore pressures and weakening the surrounding rock. An increase in pore pressure reduces the effective normal stress acting on potential fault planes. In regions already under substantial tectonic stress, this reduction can bring the rock closer to failure. Even at depths where confining pressure is high, localized zones of weakness may develop, enabling sudden slip. In this way, dehydration reactions provide a mechanism for brittle-like behavior in environments otherwise dominated by ductile flow. Beyond fluid release, the presence of hydroxyl within minerals can influence mechanical properties more broadly. Hydrated minerals often deform more readily than their dry counterparts. Variations in water content along a descending slab may create contrasts in strength, focusing strain into specific regions. As stress accumulates unevenly, it may eventually exceed the capacity of the rock to accommodate gradual creep, resulting in abrupt rupture. Some deep focus earthquakes are also associated with phase transformations. As minerals adjust to higher pressure structures, volume changes and alterations in crystal geometry can induce internal stress. When combined with the effects of dehydration, these transformations may contribute to instability within the slab. The process is complex, involving thermal gradients, compositional heterogeneity, and evolving mineral assemblages. The distribution of deep earthquakes often traces the path of subducting plates as they descend into the mantle. Their depths correspond to zones where hydrous minerals break down and where structural transitions occur. Rather than contradicting the expectation of ductile behavior at high pressure, these events reveal the nuanced interplay between chemistry and mechanics. Water, though chemically bound and invisible at these depths, influences how stress is stored and released. In this quiet interior, earthquakes are not merely expressions of tectonic motion. They are signatures of mineral reactions, of water shifting from one structural host to another, of rock adjusting to new conditions. Through their seismic waves, they offer glimpses into a hydrated mantle where strength and fragility coexist under extraordinary pressure. Beyond our own world, rocky planets orbit other stars in numbers that were once unimaginable. Telescopes now detect distant bodies by the subtle dimming of starlight or the faint wobble of stellar motion, revealing a galaxy filled with terrestrial worlds. Some are similar in size to Earth, others far larger, often described as super-Earths, with masses several times greater than our own planet. For many years, the search for habitability focused on surface conditions alone, especially whether liquid water might exist under the right balance of temperature and pressure. The recognition that vast quantities of water can be stored deep within a planet's mantle shifts this perspective. Habitability may not depend solely on oceans visible from space. A rocky planet could contain significant water integrated into high pressure minerals hidden beneath its surface. In such cases, the presence or absence of surface seas might represent only one expression of a deeper inventory shaped by internal structure and thermal evolution. On larger rocky worlds, pressure increases more rapidly with depth. This could expand the stability fields of hydrous minerals, potentially allowing even greater volumes of water to be stored within the mantle. At the same time, higher gravity and thicker lithospheres might influence whether plate tectonics can operate. If internal water reduces viscosity and facilitates mantle convection, as it does on Earth, then hydrated interiors could support long-term geological activity. Without sufficient internal water, a planet might develop a rigid outer shell, limiting heat transfer and reducing tectonic recycling. Exoplanet models now consider not only orbital distance from a star, but also bulk composition and internal dynamics. A planet located within the traditional habitable zone might still lack surface oceans if its water is sequestered deep within the mantle or lost early to space. Conversely, a world with modest surface water could possess a substantial internal reservoir that moderates climate over geological time through volcanic outgassing and carbon cycling. The idea that water can reside within minerals under extreme pressure broadens the criteria for evaluating distant worlds. Spectroscopic measurements of atmospheres may hint at volcanic activity or water vapor, but they cannot directly reveal the structure of a mantle. Understanding how water behaves at depth on Earth provides a template for interpreting the potential interiors of other planets. In this wider context, the hidden reservoir beneath our feet becomes more than a terrestrial curiosity. It becomes part of a framework for planetary science, suggesting that the distribution of water between surface and interior plays a central role in shaping geological vitality and long-term stability. The search for life beyond Earth may therefore depend not only on detecting oceans in reflected light, but on understanding how water and rock interact deep within unseen layers of distant worlds. Climate, when viewed across centuries, appears delicate and variable. When viewed across billions of years, it reveals a deeper resilience. Earth has endured shifts in solar luminosity, episodes of intense volcanism, continental rearrangements, and even global glaciations. Yet, through these upheavals, liquid water has persisted at the surface for most of the planet's history. This persistence is not solely a matter of distance from the sunday. It is tied to a slow exchange between atmosphere, ocean, crust, and mantle that regulates the concentration of carbon dioxide over immense spans of time. The long-term carbon cycle operates through a series of linked processes. Carbon dioxide in the atmosphere dissolves into rainwater, forming weak carbonic acid. As this water interacts with exposed rock, especially silicate minerals, chemical weathering occurs. Carbon becomes locked into dissolved ions that are transported by rivers to the ocean, where they eventually precipitate as carbonate sediments. Over time, these sediments are buried and incorporated into the lithosphere. Plate tectonics then carries portions of this carbon downward at subduction zones. Some of it returns to the atmosphere through volcanic outgassing, while some may remain stored in the mantle for extended periods. The rate at which carbon dioxide is removed from the atmosphere by weathering and reintroduced by volcanism influences global temperature. If atmospheric carbon dioxide rises, chemical weathering tends to accelerate in a warmer, wetter climate, drawing down carbon and cooling the planet. If carbon dioxide falls, weathering slows, allowing volcanic emissions to rebuild atmospheric concentrations. Water is central to each stage of this cycle. It enables chemical reactions between carbon dioxide and silicate minerals, transports dissolved carbon to the ocean, and influences melting processes that drive volcanic release. Deep within the mantle, hydration affects the efficiency of plate tectonics, which in turn governs how effectively carbon is recycled. Without sustained tectonic activity, the long-term regulation of carbon dioxide would falter. Over billions of years, as the sun gradually brightened, this interplay helped maintain surface temperatures within a range compatible with stable oceans. The system is not perfectly steady, and Earth has experienced dramatic climatic swings. Yet the presence of liquid water and active tectonics has provided feedback mechanisms capable of counteracting extremes. The hidden reservoir of water within the mantle contributes indirectly to this stability. By facilitating mantle convection and subduction, it supports the geological processes that recycle carbon between surface and interior. Climate, in this view, is not governed solely by atmospheric chemistry or solar radiation. It is linked to the deep structure of the planet, where water embedded in minerals helps sustain the slow circulation that has moderated Earth's environment across the vast expanse of geological time. Two neighboring planets formed from similar materials at comparable distances from a young star that was gradually brightening. One now carries vast oceans and an atmosphere shaped by cycling carbon and water. The other is shrouded in dense clouds of carbon dioxide, its surface hot enough to melt lead, its landscape sculpted by ancient lava rather than flowing rivers. The divergence between Earth and Venus is not simply a matter of proximity to the Sunday. It reflects a difference in how each world managed heat, atmosphere, and water over time. Venus likely possessed water early in its history. Geological and atmospheric models suggest that it may once have supported oceans or at least substantial surface reservoirs. As solar radiation increased and volcanic outgassing enriched the atmosphere with greenhouse gases, surface temperatures rose. Water vapor, itself, a powerful greenhouse gas, accumulated in the upper atmosphere. In a feedback loop known as a runaway greenhouse, warming led to more evaporation, which led to further warming. Eventually, water molecules in the upper atmosphere were broken apart by ultraviolet radiation, allowing hydrogen to escape into space. Without sufficient replenishment, the planet's surface water was lost. Earth faced similar early challenges. The sun's output evolved, and volcanic emissions released carbon dioxide and water vapor. Yet Earth did not cross the same irreversible threshold. Part of this resilience lies in the long-term carbon cycle that regulates atmospheric composition. Part may also lie in the distribution of water between surface and interior. With substantial water stored in hydrated minerals deep within the mantle, Earth retained a reservoir less vulnerable to atmospheric escape. If surface conditions had become temporarily extreme, some water could have been transported downward through subduction, integrated into the mantle, and later returned through volcanic outgassing. This deep storage acts not as a shield against all change, but as a buffer within the planetary system. It reduces the likelihood that all water would reside solely at the surface, exposed to runaway feedbacks and lost to space. Venus, lacking plate tectonics as observed on Earth, may not have sustained an efficient mechanism for recycling water into the interior once extreme warming began. Without a dynamic exchange between crust and mantle, and without sufficient internal hydration to moderate mechanical behavior, its evolution followed a different path. Earth's continued possession of oceans suggests that multiple stabilizing factors worked together. Internal water influenced tectonics and carbon cycling, while surface processes regulated climate over long intervals. The result was not immunity from change, but the avoidance of permanent desiccation. In the interplay between atmosphere, lithosphere, and mantle, the presence of deep water may have quietly supported the conditions that allowed Earth to remain a world of seas rather than a barren, overheated desert. Even as evidence for deep water has grown more compelling, the interior of the planet remains a realm inferred rather than directly observed. The transition zone cannot be sampled in bulk, and its hydration state must be reconstructed from seismic velocities, laboratory experiments, and rare mineral inclusions. Each method carries assumptions. Each introduces margins of error that widen as depth increases. Estimates of how much water the transition zone can hold depend on mineral composition, temperature distribution, and the extent to which subducted slabs have delivered hydrous material over geological time. Laboratory measurements suggest that minerals such as wadsleyite and ringwoodite can incorporate significant amounts of hydroxyl. Yet, those experiments occur under controlled conditions that may not perfectly replicate the heterogeneity of the mantle. Natural samples are scarce, often microscopic, and represent only small windows into a vast and variable system. Seismic interpretations add another layer of complexity. Slower wave speeds can indicate hydration, but they can also reflect higher temperatures or compositional differences unrelated to water. Distinguishing among these factors requires sophisticated modeling and dense global datasets. Even then, solutions are not unique. Multiple internal configurations can produce similar seismic signatures, leaving room for debate about the precise distribution of water at depth. Regional variation further complicates the picture. Subduction zones may introduce more water into certain sectors of the transition zone, while other regions remain comparatively dry. Mantle convection can mix materials over long timescales, but it may also preserve pockets of differing composition. The result is unlikely to be a uniformly saturated layer encircling the planet. Instead, hydration may vary laterally and vertically, forming a mosaic shaped by tectonic history. These uncertainties have not stalled research, they have guided it. New seismic arrays continue to improve resolution, allowing finer scale mapping of velocity anomalies. Advances in high-pressure mineral physics refine our understanding of how hydration alters elasticity and density. Isotopic analyses of volcanic rocks seek signatures of deep water sources, probing whether certain magmas tap reservoirs that have remained isolated for billions of years. Numerical simulations of mantle convection incorporate variable water content, exploring how hydration influences long-term circulation and chemical differentiation. As computing power increases, models grow more detailed, integrating thermodynamics, fluid migration, and mineral phase transitions within a single framework. The hidden reservoir beneath the surface is therefore not a fixed conclusion, but an evolving hypothesis supported by converging lines of evidence. Its scale and distribution remain subjects of careful scrutiny. The interior of the planet still holds unanswered questions, and each new dataset reshapes the contours of understanding. Knowledge advances gradually, not by erasing uncertainty, but by narrowing it, revealing a deep Earth that is more intricate and dynamic than earlier generations imagined. Across the planet, instruments continue to listen. Seismometers anchored to bedrock record vibrations from distant earthquakes, capturing subtle variations in the way waves traverse the interior. As networks expand and become more densely distributed, their collective sensitivity increases. Regions once sparsely monitored are now part of global arrays, capable of resolving finer details in wave speed and attenuation. With each additional station, the interior image sharpens, not through sight, but through accumulated resonance. Advances in global tomography build upon this expanding data set. By integrating signals from earthquakes occurring at different depths and locations, scientists construct increasingly detailed three-dimensional models of the mantle. Variations in velocity are mapped with greater precision, allowing hydration signatures to be distinguished more confidently from temperature anomalies. Improvements in inversion algorithms reduce ambiguity, narrowing the range of possible internal structures that fit observed data. The result is not a photograph, but a progressively refined portrait shaped by mathematics and measurement. Laboratory techniques continue to evolve as well. Diamond anvil cells now achieve pressures and temperatures that more closely approximate conditions in the transition zone and lower mantle. Synchrotron radiation facilities provide intense beams of X-rays capable of probing crystal structures at microscopic scales while samples remain under compression. Spectroscopic methods detect hydrogen within minerals with increasing sensitivity, clarifying how much water can be stored under varying conditions. These experimental advances translate theoretical stability fields into measurable behavior. Parallel to these efforts, numerical modeling grows more sophisticated. Deep mantle simulations incorporate thermodynamics, fluid migration, phase transitions, and convection within a unified computational framework. By adjusting water content and tracking its influence on density, viscosity, and melting, researchers explore how hydration shapes long-term planetary evolution. Such models test scenarios over spans of hundreds of millions of years, revealing how deep reservoirs may interact with surface processes. Future satellite missions may refine measurements of Earth's gravity field, detecting subtle mass redistributions linked to mantle dynamics. Combined with seismic and laboratory data, these observations could constrain the distribution of hydrated minerals more tightly. Integrated approaches, drawing from geochemistry, mineral physics, and geodynamics, aim to reduce uncertainty and reveal patterns that single methods cannot resolve alone. The deep reservoir remains beyond direct reach, yet the tools designed to understand it grow more capable each decade. As instrumentation improves and datasets expand, the interior becomes less abstract. Each refinement adds nuance to the evolving image of a hydrated mantle, suggesting that the story of hidden water is not static, but unfolding through the quiet convergence of technology, theory, and observation. Deep beneath the shifting plates and rising volcanoes, the mantle does not remain still. Though solid in composition, it flows with a patience that defies ordinary intuition. Heat from the core and from radioactive decay drives convection, setting vast regions of rock into motion. Warmer material rises slowly toward the surface, while cooler, denser portions sink. This circulation unfolds at rates measured not in meters per second, but in centimeters per year, carrying minerals and the water bound within them through immense loops that span much of the planet's interior. Water integrated into high-pressure minerals becomes part of this convective rhythm. When oceanic plates descend, they transport hydroxyl into deeper layers. Portions of that water are released, and returned upward through volcanism, yet some remain stored in the transition zone or are carried even further into the lower mantle. Over time, convective currents redistribute these materials, mixing hydrated and relatively dry domains, shaping the chemical structure of the interior. The timescales involved are difficult to grasp. A parcel of mantle material may take hundreds of millions of years to complete a single circuit from depth to near the surface and back again. During that journey, minerals transform as pressure and temperature conditions change. Water may shift between structural hosts, released in one environment and reincorporated in another. The process is continuous, yet so gradual that it leaves no immediate trace on human history. This slow circulation influences the long-term stability of oceans and atmosphere. By regulating the exchange of water and volatiles between surface and interior, mantle convection acts as a deep reservoir and conveyor. It does not respond quickly to transient climate shifts or short-lived tectonic events. Instead, it operates on geological epochs, smoothing extremes through sustained recycling. The metaphor of a planet breathing emerges naturally from this pattern. Subduction draws material inward, like an inhalation extending into the mantle. Volcanism and ridge activity release volatiles back to the surface, an exhalation expressed in steam and lava. Yet this breath is measured in hundreds of millions of years, far slower than any biological rhythm. It is a structural exchange embedded in the physics of convection and mineral stability. Through this enduring motion, water never remains confined to a single domain for long in geological terms. It migrates between ocean, crust, and mantle, guided by temperature gradients and pressure thresholds. The hidden reservoir, deep below, participates in this cycle, not as a static storehouse, but as a dynamic component of a slowly circulating system. In that vast interior flow, the story of water continues, carried forward by the steady movement of rock itself. Life, in all its fragile complexity, rests upon a simple requirement. Liquid water must remain available at the surface for vast stretches of time. Cells rely on it as solvent and scaffold. Ecosystems depend on its steady circulation between ocean, atmosphere, and land. Yet the persistence of this surface water across billions of years has not been guaranteed by sunlight and distance alone. Beneath the biosphere, processes unfolding in darkness have helped maintain the stability that life requires. The deep mantle, with its capacity to store water within mineral structures, acts as a long-term moderator. When tectonic plates descend, they transport water into the interior, reducing the amount exposed to immediate atmospheric loss. When volcanic systems release water vapor and other volatiles, they replenish the surface inventory. This exchange is not rapid enough to influence seasonal droughts or even glacial cycles. It operates across epochs, smoothing extremes that might otherwise accumulate unchecked. Stable surface water depends on balanced climate, and climate depends in part on the carbon cycle regulated by plate tectonics. Deep hydration influences mantle convection and subduction, sustaining the recycling of carbon between atmosphere and interior. Without that sustained geological activity, atmospheric carbon dioxide might drift toward levels incompatible with long-term habitability. The deep reservoir of water, though hidden from view, supports the mechanical and chemical conditions that enable this regulation. Through planetary history, Earth has endured asteroid impacts, shifts in solar luminosity, and episodes of global glaciation. Oceans have expanded and retreated, ice has advanced and melted, Yet the planet has not remained locked in permanent freeze, nor slipped irreversibly into runaway greenhouse conditions. The interplay between surface processes and deep storage has contributed to this resilience. Water bound within mantle minerals provides a buffer against sudden loss, ensuring that the hydrosphere is not confined solely to the atmosphere and oceans. When compared with neighboring worlds that lack either sustained tectonics or substantial internal hydration, Earth's path appears distinct. The presence of deep water does not guarantee life, yet it strengthens the framework within which life can endure. It connects biological stability to geological circulation, linking ecosystems at the surface to mineral transformations far below. In this sense, the hidden ocean is not merely a geophysical curiosity. It is part of the architecture that has allowed oceans to persist, climates to remain within workable bounds, and living systems to evolve over immense spans of time. Beneath forests and reefs, beneath cities and deserts, water resides in stone, participating in a slow planetary rhythm that has quietly supported habitability since the earliest chapters of Earth's history. From orbit, Earth appears serene. Swirls of cloud drift across blue oceans, continents stretch in familiar outlines, polar ice gleams in quiet symmetry. The surface presents a coherent image, as though the planet were defined by what light touches. Yet beneath this thin, illuminated skin lies a structure layered in depth, pressure, and transformation, a system far more intricate than the calm exterior suggests. The crust upon which forests grow and cities stand is only a fragile veneer, varying in thickness but insignificant compared to the mantle below. Beneath it extends a vast domain of silicate rock, convecting slowly, reshaping itself under heat and gravity. Within that mantle are boundaries, where minerals alter their internal arrangements, where density shifts and chemical capacities change. Water, bound invisibly into crystal lattices, participates in this hidden architecture, influencing melting, deformation, and circulation without ever forming a visible sea. The planet is not a simple sphere of uniform material. It is stratified, each layer governed by distinct physical conditions. The lithosphere fractures into plates that migrate across the surface. The asthenosphere beneath yields gradually, accommodating motion through slow creep. Deeper still, the transition zone stores and releases water in response to pressure thresholds. The lower mantle, dense and expansive, carries heat upward from the core. At the center, iron crystallizes under compression beyond ordinary imagination. Each level interacts with those above and below, forming a continuous exchange rather than isolated compartments. Surface phenomena that appear separate are rooted in this internal complexity. Mountain building reflects the convergence of plates driven by mantle convection. Volcanic arcs arise from dehydration reactions deep within subducting slabs. Climate stability depends on tectonic recycling influenced by hydrated minerals. Even the persistence of oceans is linked to reservoirs concealed far beneath the crust. The visible world rests upon processes unfolding in darkness, guided by thermodynamics and mineral physics. What once seemed complete when measured only by ocean volume and atmospheric composition now appears part of a larger system extending inward. The hydrosphere is not confined to waves and clouds, it connects to rock at depth. The atmosphere does not float independently, it exchanges material with volcanoes rooted in the mantle. The biosphere depends on stability sustained by convective motion, invisible from above. As understanding deepens, the planet reveals itself as layered in both structure and story. The calm surface is supported by an interior in motion, shaped by gradients of pressure and temperature that reorganize matter across immense spans of time. Earth is not merely a surface world adorned with oceans and continents. It is a complex system whose visible simplicity rests upon hidden processes circulating quietly beneath our feet. Certainty fades gradually as depth increases. For all that has been inferred about hydrated minerals and slowed seismic waves, the precise quantity of water stored within the mantle remains unresolved. Estimates rely on indirect measurements, laboratory constraints, and models that must assume temperature and composition at scales no instrument can directly verify. The transition zone may hold water equivalent to a vast ocean, or it may contain significantly less, distributed unevenly through complex structures shaped by tectonic history. Distribution patterns are particularly difficult to constrain. Subducting slabs introduce water along specific pathways, yet mantle convection can stretch, fold, and disperse these hydrated domains over immense distances. Some regions may be relatively enriched, while others remain comparatively dry. The degree to which mixing homogenizes the interior over billions of years is still debated. Seismic tomography reveals variations in velocity, but translating those variations into detailed hydration maps requires assumptions that are continually refined. Beyond quantity and distribution lies the chemistry of the deep mantle itself. High-pressure experiments demonstrate how individual minerals respond to hydration, yet the mantle is not composed of a single phase. It contains assemblages that shift with depth and temperature, each with its own capacity for incorporating hydroxyl. The interactions among these phases, especially under varying thermal conditions, remain areas of active investigation. Questions persist about how water influences phase boundaries, melting relations, and the long-term evolution of mantle composition. There is also uncertainty regarding the exchange rate between surface and interior. While subduction and volcanism clearly connect the two realms, the balance between water carried downward and water returned upward over geological time is not precisely known. Variations in tectonic style through Earth's history may have altered this balance, affecting how much water accumulated in deep reservoirs versus how much remained at the surface. Even the lower mantle, extending far beneath the transition zone, invites speculation. The stability of hydrous phases under the extreme pressures found there is still being explored. Some experiments suggest that certain minerals may host hydrogen deeper than previously assumed, while others indicate limited storage capacity. The true extent of hydration at these depths remains uncertain. Scientific understanding advances by narrowing such uncertainties rather than eliminating them entirely. Each new dataset refines models, and each experiment tests assumptions embedded in earlier interpretations. The hidden reservoir beneath the crust is supported by converging evidence, yet its full character is not fixed. The interior of the planet continues to guard details of its composition and circulation, reminding us that even with global networks and high-pressure laboratories, the deep Earth retains elements of mystery that invite continued exploration. Most days pass with no awareness of what lies beneath our steps. Pavement warms in sunlight, soil absorbs rain, mountains hold their shape against the horizon. The ground feels solid and complete, a stable foundation for everything that lives above it. Yet stability at the surface rests upon gradients of pressure and temperature that increase steadily with depth, compressing rock into forms far removed from anything familiar. A few kilometers down, stone grows warmer and more ductile. Far below that, pressure rises beyond ordinary comparison, reshaping minerals at the atomic scale. Crystal structures tighten, Atoms shift into denser configurations, and hydrogen becomes incorporated within lattices never seen at the surface. Water there is not pooled in darkness, nor gathered in hidden caverns. It is held in bonds, integrated into the very framework of silicate minerals, preserved under conditions of immense compression. The continents stand upon this layered interior, supported by mantle that moves with slow persistence. Convection circulates heat upward from the deep interior, guiding plates across the globe over spans measured in hundreds of millions of years. Within those motions, water descends with sinking slabs and returns through volcanic arcs, part of a cycle extending far beyond rivers and clouds. What appears static above is sustained by exchange below. This reservoir within stone does not shimmer or reflect light. It cannot be sailed upon or mapped by shoreline. Its presence is inferred through seismic waves, laboratory experiments, and minerals carried upward in rare geological moments. It is ancient in parts, perhaps older than the oceans that define the planet's face. It occupies a realm where pressure alters behavior and where chemistry unfolds under constraints unlike any at the surface. To consider this hidden store is to recognize that Earth's water is not confined to what glitters in sunlight. The hydrosphere extends downward into rock, braided into the mantle's fabric. The planet safeguards portions of its water deep within its interior, buffering change and sustaining processes that shape climate, tectonics, and habitability across vast stretches of time. The world we inhabit is therefore more than a thin blue shell wrapped around stone. It is a layered system in which visible and invisible reservoirs interact. Beneath forests and cities, beneath oceans and ice, there exists a depth where minerals cradle water within their structure, where motion continues without spectacle, and where circulation persists beyond human timescales. The Earth is not solely a surface world defined by coastlines and skies. It is dynamic through its entire body, storing and transferring water within its own mineral framework. Far below where light has ever reached, the planet continues its slow internal exchange, steady and unhurried, carrying ancient water through stone in cycles that endure long beyond a single human lifetime.